All right, so we just finished talking about how, we used to go from position to velocity to acceleration taking derivatives, and the reverse route is via integrals. And so let's talk about integrals now. Usually, when we talk about integrals, right, that's one way to express what we call net change over time. Net change over time. So, this particle was going back and forth, back and forth. It had, what was the net change? What was the displacement over time? That is an integral. All right. Okay. So the best example to see this is when we talk about particle motion. So let's talk about particle motion on the interval A to B. So what that means is this particle is literally moving back and forth in that region of A to B. Okay? All right, let's recall a couple of things. When the velocity is positive, we say the particle is moving to the right. That is the only way to know. So if you remember in the chapter 5 tests, we had this question, right? What is is the particle moving to the left or right at t equals 2? And, you would say left, and then what was the reason? And there was, oh my, so many different versions of the reason, right? It is positive. Way, right? There is one way to say whether the particle is moving to the left or right, and that is the velocity is positive or the velocity is negative. Anything else, I will not accept it. Okay. All right. Displacement. That's the next piece. Displacement is how much the particle has moved, and we find that by taking the integral of the velocity from A to B. Okay? All right. If you take the integral of the velocity, what does that give you? So if you see here, if you take the integral of the velocity, what does that give you? That gives you the position. So when you integrate anything, right? Okay, so you got the position. Now, when you integrate over a closed interval, what do you do then? You plug in A and B. So what does that give you? S, position of B, minus S of A. So let's think about that. You integrate velocity, you end up with final position minus initial position. Is that or is that not displacement?
It is.
That's displacement, right? So final position minus initial is what you get. All right, so it's built into the formula. Yeah.
We still do the same thing for substitution as well.
Yeah. That's a technique of integration, right?
Would we use
It's all the same.
substitution?
You can, of course, you can. It depends on the function.
Okay.
All right. So now we talked about earlier about final position, right? And how did we find final position? Well, we said that was the initial position, right? The initial position plus the displacement. All right, so that's final position. All right, if final position is S of B, then how do we find it? It's S of A, that's the initial position, plus, how do we find displacement? It's the integral A to B, V of t dt. All right, is this exactly what we just talked about on that number line with that little particle going back and forth from -2 to 6 to 8 to whatever? Yeah. It was where it was before at -2 plus how much was it displaced? +8, right? And now it's at +6. And now, how do you find the total distance? Well, that's the absolute value. Okay, that's the integral of the absolute value of the velocity. All right, so remember that it's not absolute value afterwards. It's the integral of the absolute value. Okay. All right, let's take a look at some examples here. All right, the function v of t is the velocity in meters per second of a particle moving along the x-axis. So we've got units here, meters per second. Use analytic methods to do each of the following. Determine when the particle is moving to the right, to the left, and stopped. Okay, so how do we know that the particle is moving right or left? What do we need to look for? If what is positive or negative?
Velocity.
Velocity. Let's not use pronouns, right? Say the exact thing, not it, but the velocity. Okay, so for part A, we want to set v of t equal to 0. So that means 0 is equal to 24 minus 3t. T is equal to 8. At t equals 8, how much is the velocity? It stopped, right? So it stopped at t equals 8. So now, this is over the interval of 0 to 10. So when you do your number line, you have to make sure to go from 0, why can't I? To 10. And then 8 is right about here. Okay. Between 0 and 8, is the velocity positive or negative? Like when t equals 1, it's positive, and then here, it's negative. So it's moving to the right from 0 to 8. It's not moving anywhere at 8, so that's an open interval, right? And then it's moving left from 8 to 10. Okay? You see where it's open and where it's closed? Yeah? Okay. Next, we need displacement. Find the particle's displacement for the given time interval. If s of 0 is equal to 3, what is the particle's final position? So we're looking for two things, displacement and final position. Well, okay, displacement is the integral of the velocity, right? So displacement is the integral from 0 to 10 of v of t, which is 24 minus 3t dt. So now, physics says integrate velocity to get displacement. Then, when you're integrating, right, the techniques that you use, that's up to you. Do you have to do substitution? Do you have to not do substitution? What else are you doing? I don't know. Okay. All right. So, let's do this. When I integrate, I get 24t minus 3t squared over 2. And we're going to go from 0 to 10. So the 0 is not going to count for anything. And then when you put in the 10, you get 90 meters. So that's the displacement. What does that mean? What does that mean? You guys all said different things, but you all said the same thing, right? So in the time, basically, during the time interval 0 to 10, this thing is now 90 meters to the right of where it was originally, right? Okay. So then we need to find the final position. Final position. Okay, so here's how I want you guys to write this. Final position is initial position s of 0 plus 0 to 10 v of t dt. I want to see this because I want to know if you know what you're doing. Okay? So initial position plus displacement. Initial position is 3 plus 90. That's equal to 93 meters. So that's the final position. All right? Don't skimp on the work here. All right? Give me all you got. Yeah.
So you want us to write that final position
Uh-huh. S of 0. Because that's what we are given here, the initial position at t equals 0.
So are we taking S of 0?
Well, in order to find final position, you should know initial position. It was given to me. S of 0. Okay, so now C asks the total distance traveled. Okay, so total distance is equal to what? Of 24 minus 3t dt. Okay. I never taught you how to find the integral of the absolute value of a function. That's actually really, really cool. But for this, we're going to use our calculators. All right? So when you put it in your calculator, so remind me again, do you guys have the Inspire or the 84s? The older one. Okay.
Yeah, how do we get integrals on our calculator?
I'll tell you. We never did it? We did it.
It's math 9.
Yeah, it's math 9. So you're going to do math 9.
Oh, there we go.
Right? And we're going to go from 0 to 10. And now it's the absolute value. So that's math number 1. Right? And it's 24 minus 3t, or x. Yeah. X dx. In the older version, right, where you get the parentheses, not the math print here, you're going to do the function integrate. Your absolute value is the same way. You do math 9, I believe. You do, and then for absolute value math, you press the right tab for the number tab, and it's the first one, absolute value. You're going to put in, no, first you're going to put in the function 24 minus 3t, 24 minus whatever, 3x. Okay, so this is what we're going to get here. All right, 101.99999, which is about 102. So let me show you how to do it. 102 meters. So in the other format, it's function integrate, and then you do, absolute value, 24 minus 3t, close the parentheses, comma, I'm sorry, you're going to do x, not t. With respect to x, comma, from 0 to 10. That's how you do it. That's on the old calculator. All right, that's on the... Okay, yeah, Jackson. Let's see what else we got here. The function v of t is the velocity in meters per second of a particle moving along the x-axis. Use analytic methods to find more of the same. So when is the particle moving to the right, left, and stopped, right? So now, okay, let's take a look at what we have. We have v of t equals sine of t. So this is a particle that's oscillating, right? It's going back and forth. Determine when the particle is moving to the right, to the left, and stop. So what are we going to do? And it goes from 0 to 2 pi, right? So for part A, we're going to set this equal to 0. And when is sine of t equal to 0 these days? More than once. So when is that? At 0? When else? Pi? 2 pi. So t is equal to 0, pi, 2 pi, right? Remember the sine curve? It's at 0, pi, and 2 pi. Huh? That's that's a good way to think about it. Yeah.
Let's just say that you blanked out. Is there no other way to get C 0 to
Unit circle? I mean, if you have your calculator, sure, you could graph sine. You could say like inverse sine of 0. But if you do inverse sine of 0, it's only going to give you 0. It's not going to give you pi and 2 pi. That's where you, the human, comes in, right? Yeah. This is a really good representation, okay? Because it goes from 0 to 2 pi, and that's what it looks like. All right. And any excuse to draw a sine graph is really, right? Okay. So this is where it stopped. And we're going to go from 0 to 2 pi, and pi is in the middle. So it's 0 at 0, pi, 2 pi. Now, that little graph of mine is going to help me even more, right? Because look, according to my graph, sine is positive. It's above the x-axis. It's positive from 0 to pi, and then it's below the x-axis, so it's negative from pi to 2 pi. How cool is that? Like 3 birds and 1 stone. I'm sure there is another one in there that we could use it for, right? All right, and don't forget that this is v of t we're looking at. So this is moving to the right. From 0 to pi. Okay, so do we open or close at 0? Is it open or close at 0? Why close, why open? It's not closed, it's open, but why? Because it's stopped. You see that in this case? Like in the case before, it was only stopped at 8. But now it's also stopped at 0, so it's not moving anywhere.
Why don't we go even more negative and even more positive?
Huh?
Oh, never mind.
And then it's moving to the left from pi to 2 pi. Yes.
For the other one, let's stop at, oh, never mind.
Yeah. Yeah.
So for this one, since it doesn't stop, since it stops at 0 and pi, it's open.
Mm-hmm.
But for the other ones, it only stopped one time.
Mm-hmm. Yeah, technically it was moving at 0. We just started timing it. We started timing it then, but it was moving.
Oh, so then it stopped at 8. It's open. Okay.
Yeah. Yeah. Okay. All right. So that's how it's moving to the left or to the right. All right. So B says, what is the displacement if S of 0 is 1, right? Here is where we're given S of 0. Yes.
If it doesn't give us the bounds, then we not do this problem.
Well,
or if it gives us different bounds.
If it, like in this particular problem, you would say it stops at like every pi.
Right, but what if it was like 1, 2,
It usually won't.
3?
It usually won't, because you'll usually be given enough of a, you'll usually be given, like, or you'll say, you know, if this particle is moving for 10 seconds, or what happens in the first 2 seconds. Okay? All right, so displacement is going to go from, it's the integral of velocity from 0 to 2 pi, right? And this is why we learned what the integral of sine of t is, which is cosine of t, right? Yeah? Am I right?
No,
it's negative. Thank you. Just checking. Negative cosine of t, and we're going to go from 0 to 2 pi. So that's going to be negative, all right, let's do this. Cosine of 2 pi minus cosine of 0. What's cosine of 2 pi?
Or 1.
Tell me, is it negative 1 or positive 1? It's 1 because it goes back. So 1 minus what's cosine of 0?
1.
Also 1. So it's 0. So the displacement is 0 meters. So that means this particle never moved?
No, it finished where it started.
Does that make sense that it, why does it make sense? Because it's oscillating, because look, it's moving to the right the same amount of time as it's moving to the left, right? And this is constant velocity. So it moved to the right, and then it stopped, and then it moved to the left the same amount. Like, look at how cool this is. You guys aren't as excited. I don't know why. All right, so that's the displacement, okay? The final position then is equal to, okay, so here's another way you can say this. The final position is S at 2 pi. Is that right? So yet another way of for notation. That's S of 0 plus the integral from 0 to 2 pi v of t dt. Initial position plus displacement. That is 1 plus 0. So S at 2 pi is 1 meters. And then C, huh? Well, the initial position was 1, but then the total displacement is 0. So it started at 1, moved to the left, moved to the right, moved to the right, and moved to the left. You're forgetting to add the initial position, Jason. So this, it's S of 0 plus what you get from the integral. Oh, You should have said so before. It's not 1 though. It's not, it can't be, I'm sorry, it can't be 0 because we know that it moved and then it moved back. So that's gonna be, what is it? It's the total distance is the integral from 0 to 2 pi, absolute value of sine of t dt. All right, who's gonna tell me how much that is? Huh?
4 meters.
Is it?
Yeah.
4 meters.
It does not make sense if it's like going down.
Well, technically it's not a triangle, but yeah. Okay. The way you integrate by hand is you figure out where it's positive and then you just integrate from 0 to 2 pi, and then it's negative here, so you do minus, and then you move it up. So it's not that complicated, but maybe we could do it afterwards because we've got some time.
You said this is the last chapter?
Right, but then we're gonna have some extra time in the end of the Okay. Here we go. Example 3. A car moving with initial velocity of 5 miles per hour accelerates. Okay, so now we've got acceleration at a rate of 2.4 t for 8 seconds. So now it says how fast is the car going? So you need to find velocity. Okay. All right, so take a look though. It was initially moving with an initial velocity of 5 miles per hour. So it was going at 5 miles an hour, and then it started accelerating, right? And how fast is it going now? So when it started accelerating, it didn't start at 0, right? It already started at an initial velocity. So it's the initial velocity plus how much more was added to it through the acceleration. All right? So, all right, so let's do this. We are given, what are we given? V of 0 is equal to 5. And then we need to find final velocity. Okay? So, final velocity is V of 8. All right, so what is V of 8? V of 8 is V of 0 plus however much velocity this thing accrued from 0 to 8. All right? And that is, okay, so from 0 to 8, all right? When you integrate the velocity, you get, when you integrate the acceleration, that gives you the added velocity, and then you have to add it to this. Okay? All right. So what was the initial velocity? 5 plus from 0 to 8, 2.4 t dt. This is 5 plus this one. It's going to be 2.4 t squared over 2, 1.2 t from 0 to 8, t squared. So that's going to be 5 plus 1.28 squared minus 0. And that is 81.8 miles per hour. Okay? Questions? Yeah. Okay. All right. So now part B. So I'm philosophically opposed to writing MPH. just because it doesn't show the math. Anywho, all right, V of t. What is this? How far? Okay, so look at what this says. How far did the car travel
Total distance.
during those 8 seconds? Wait.
Is that total